Hey, Algebra 2 students, this is a first lesson on probability here. So we're going to be doing probability for the next few weeks here. We're finally done with sequences and series. That took us about probably about a month to get through there, but thank you for those of you who are still continuing to work hard, submit all your assignments and tests and quizzes. So probability is going to have a very different feel for us. And the first thing that you're seeing right here is actually just what a deck of cards look like. And I would say from year to year, I find that more and more students don't play card games anymore, which is a little bit sad to me because I feel like it was a big part of my childhood and I still like playing cards to this day. But if you don't typically play card games, what better time than now during this quarantine to pick up a deck of cards? I'm sure you might have one lying around at home and play a card game with the family or something like that. So I made a note down here that since my color, since I have a black and white version here, that these two rows would be red. So again, if you really have limited experience with playing cards, not a big deal, but there are questions that we'll see very often in our probability unit that have to deal with these decks of cards. So at the bottom of this information sheet, I have the total number of cards in a deck, because that will be important to us when we calculate some probabilities. How many are black and how many are red. So it's half that are black, half that are red, which would be 26 each. It's broken down into 4 different suits. We have clubs, spades, hearts, and diamonds. Okay. And then finally, we have, if we talk about face cards ever, the face cards are the jacks, queens, and kings at the end here. There's a total of 12 of those in a deck of cards in case I ask you about anything like that. And by the way, the hearts and diamonds, those are the ones that are red. The clubs and spades are the ones that are at the top here. These are the ones that are black. Okay, so clubs, spades, hearts, and then finally diamonds. Okay, we may have to come back to that later on when we talk about some of the cards here, but in our introduction to probability, we're going to talk about things called sample space, counting principle, and then by the end of the lesson, we'll be computing what are called some pretty basic probability examples. Okay. So what is a sample space? A sample space is the set of all possible outcomes. So for example, if I said rolling a die, there'd be 6 outcomes. It would be 1, 2, 3, 4, 5, 6. And in fact, the first example is going to have us list the sample space for all the possible outcomes when rolling 2 dice. Okay. So there's 2 different ways that we typically represent sample spaces. One is list pairings, which I'll show you in a moment here. The other would be through a tree diagram. So like I was saying, this first example, it says find or make a tree diagram to represent the different outcomes that are possible when rolling 2 dice. How many possible different outcomes are there? So I'll tell you, I actually skipped tree diagram for this one because it would take up a lot of space. I actually did it in a list pairings form. I think it's probably a little bit easier to do list pairings for this one, but I'll show you what I did kind of one step at a time here. I said, all right, what if I got a 1 on the first die, and then on the other I got anything 1 through 6? Those would be 6 cases that could happen. I could get a 1, 1, a 1, 2, a 1, 3, and so on. But here's another set of cases where the first number on the die was a 2, and the other number was anything 1 through 6. Moving on, if I continue to build that pattern, you can kind of see that depending on what number I get for the first roll of the die, pairing that with the numbers 1 through 6, get me all these different list pairings. So there's a lot of them there, okay? So at the end of the day, the total number of list pairings is that there are 36 possible outcomes when we roll 2 die. And in fact, in certain casino games, I think, for example, the game of craps in casino, it has to deal with the sum of the dice that you roll. And the most popular sum you can get when you roll 2 die is 7. So sometimes when we're talking about rolling 2 dice, we might be concerned with what the sum of those numbers is and how that relates to probability. Okay, the second example, I am going to use a tree diagram. It's about making a sandwich. I actually just ate lunch, so this is appropriate here. So Sarah's making a sandwich for a picnic with her friends. She has 2 different kinds of bread. She has white and wheat. She has 4 different meats: ham, tuna, roast beef, and turkey, and 3 different cheeses: American, Swiss, and provolone. Draw a tree diagram to represent the sample space and determine the number of different sandwiches that can be made with one bread, one type of meat, and one cheese. So tree diagrams, I'm hoping, is something you're familiar with from potentially middle school, because middle school you do some basic probability as well. We will definitely extend beyond what you would have learned in middle school probability. But I'll tell you that the title of my tree diagram here is sandwiches. Once I do that, I branched off and I said, well, from there I can pick a bread first, white or wheat. After I pick the white or wheat bread, I can then pick one of the 4 meat options, which was ham. I did TN for tuna and TK for turkey over here. And then the RB was roast beef. Okay, so after the bread, we have those 4 options. But then from each of those 4 options, there needs to be 3 branches for a choice of cheese. So this is what the total tree diagram would look like for building a sandwich at this picnic. And if you look at the bottom of all the branches, and you were to add up all of these possibilities going across the bottom row, that would be one complete sandwich going down each of the branches in the tree diagram. There winds up being, in this one, 24 possible outcomes. So again, a lot of outcomes that are possible here. And you can imagine that if I added in, another option for bread and maybe, 2 more meat options and another cheese, that tree diagrams are going to take a long time to complete if I want to just determine what is the total number of possible outcomes. So what that brings me to is something today called the counting principle. And you guys hopefully know the deal by now, that if anything goes too fast, just hit pause, get caught up, and then go from there. So what is the counting principle? The counting principle says if one event can occur in X number of ways and another event can occur in Y number of ways, then they can both occur in X times Y number of ways. And the reason why this is useful is, like I was saying, if you want to just know the total number of possible outcomes, what you can do is you can multiply the number of options in each of your events. So the events might be picking a bread, picking a meat, picking a cheese. If you multiply those options together, you're going to get the total number of outcomes that are possible within your sample space. So this first question says, we'll use the last example, use that picnic example with Sarah to figure out, how could we also confirm that we have 24 outcomes? So there was 2 options for bread, 4 options for the meat, 3 options for cheese. If you do 2 times 4, that's 8, and then times 3 is 24. The rest of the questions that follow are slightly different examples of the same concept with the counting principle. So here's an example. If I want to build an ice cream sundae that has 5 flavors to choose from and 6 toppings, it is sort of important to note that this only would work if you have 1 flavor and 1 topping that you can choose. Once you start choosing more than 1 flavor or more than 1 topping, it gets a little bit more complicated. But if I'm just choosing 1 of each, 5 times 6 would be 30 options possible for different sundaes. And that's probably not really even too realistic, right? If we think about going into an ice cream store or an ice cream shop, there's so many more possibilities than 5 flavors and 6 toppings that, in the grand scheme of things, you'd probably have hundreds and hundreds of options if you're only picking 1 flavor and 1 topping. Okay, next one says there are 3 entrances to a school. There are 2 stairways that go to the top floor. How many different ways can a student enter the school and go to the top floor? So I wanted to throw this one in there because I'm sure you're missing coming to the 2nd floor of school. So how many ways could you get to our classroom if we were allowed back at school? Well, in this case, 6 ways. Okay, so 3 entrances times 2 stairways. And think about our school. There's actually probably many more options than just 6. So I guess this would just be a smaller school. And finally, this last one is, the number of possible outfits that somebody can make based on the number of, in this case, a man has 8 shirts, 5 pairs of pants, and 6 ties. How many different outfits can he wear, consisting of 1 of each? 1 shirt, 1 pair of pants, and 1 tie. We're assuming in the scenario that the man does not care if he matches or not, right? I guess in the real world, you'd probably pick shirt, pants, and tie that maybe all sort of match. But if you multiply those possibilities, 8 times 5 times 6, there would be 240 ways, assuming that all possibilities nicely match one another. So I was thinking about my own personal wardrobe and I should probably do some cleaning out of my closet while I'm stuck at home here. But I said for me, I would estimate that maybe I had 20 shirts, 15 pairs of pants, and at least 100 ties. That's probably an underestimate. So for me, if I multiplied my possibilities together, assuming all of them would match, I would have 30,000 options of how I could get dressed in the morning. So it's a good thing I don't spend too much time doing that these days. But yeah, there's a lot of different possibilities of how you could make an outfit consisting of one of each of those. I also kind of think about counting principle a lot when I hear a commercial for, I feel like for some reason Applebee's stands out to me. So they say, now we have over 200 menu options or something like that. And how do they get the 200 menu options? They might say, all right, you get an appetizer, an entree, and a dessert. So if you take the number of appetizers they're offering times the number of entrees times the number of desserts, that's kind of how they determine that number of possible outcomes for the different meals that you can have at a restaurant like that. Okay, so now that we have counting principle under control, which tells us the number of possible outcomes we can come up with, we're now going to start looking at what probability represents. Okay, so we have some vocabulary at the bottom here. First thing it says a trial, and this is all filled in for you, but I'm giving you some examples off to the side. So a trial is a single attempt at doing something. So my kind of quick basic example is tossing a coin. The outcome is the result of the trial. So maybe you're looking to get heads when you toss the coin. An experiment would be repeating that trial a certain number of times. So if I said toss the coin 10 times, now it becomes an experiment. A fair or unbiased object is an object that is fair when different results have an equal chance of happening. So I think the best way to think of that is for a coin, you should get a heads 50% of the time and a tails 50% of the time. But meanwhile, if you have a coin that's biased, it gives one result a better chance of happening than another. So that would be maybe a coin that has heads on both sides. That wouldn't be so fair. If I said, hey, choose heads or tails. There's also things called weighted coins. Maybe it's more likely to get heads or tails depending on which side is more heavily weighted. So a couple different things that would make an object biased potentially. If I had if I gave you some dice to roll and I somehow took off the number 4 and I replaced it with another number 3, that would be a biased object. It's more likely you're going to get a 3 now and impossible to get the number 4. So a couple things that we can relate to as far as that goes. Okay, on the last page. I'm going to start filling some of this in with you. We're going to go through quickly and fill in the information about what to remember in a deck of cards at the top, and then I'll show you how we're going to calculate some probabilities. Okay. So things to remember about cards. Number in a deck is that there's 52 cards total in the deck. The number of suits, there are 4 suits total. We have hearts, diamonds, clubs, and spades. The number of cards in each suit, if you do 52 divided by the 4 suits, there would be 13 cards in each suit. Number of red, half the deck is red, so that's 26. The other half is black, so we got 26 black. And finally, the number of face cards is, I mentioned that before, that's 12. Face cards are anything with a picture on it, like the jack, the queen, and the king. Since there's 4 of each of those, we get a total of 12 there. Okay. So to find the probability of a single event occurring, what we're going to do is we're going to take the number in the event and divide it by the number total in the sample space. So what I mean by that is we're going to look at an example where we're rolling a numbered die. Okay. So if we're rolling some dice here, or rolling just one numbered die, the number total in that sample space is that there's 6 numbers possible. So the denominator should always be something out of 6 in this first one. If I look at choosing a card from a deck of cards, the number on the bottom should always be 52. The top is the number in the event that we're looking to happen. So for example, in this part A, the probability of getting a 3 Since there's only one number 3 on the die, it's going to be 1 out of 6. The probability that I roll an even number. So remember that the total, the number of outcomes is anything 1 through 6 here. The evens would be 2, 4, and 6. So there are 3 evens out of 6 in the sample space. I realize that that reduces to 1/2. So feel free to reduce fractions when you want to, but that will not be an expectation in this unit that you reduce the fractions. So I'm actually just going to leave it as 3 over 6 to make it a little bit easier for myself. And just know that when I'm rolling a die, the denominator is always 6. Probability of a prime number. I'll tell you, primes are one thing that students do often mix up when they're looking at this list. The primes in the list are 2, 3, and 5. So if you were thinking 1 is prime, it's actually, by definition, numbers bigger than 1, such that the only factors are 1 in itself. Okay, so that would also be 3 out of 6, but just don't include 1 in your list of primes. Numbers that are greater than 4. Greater than 4, I only have 5 and 6 in the list, so it would be 2 out of the 6 on the die are greater than 4. Don't include 4 because it didn't say greater than or equal to. Probably that I roll a 7. Well, there's definitely no 7s on the die, so I would say 0 out of 6, or I can actually pretty clearly say that this is just 0. And the last one, probably that the number is less than 7. Well, all of the numbers in the sample space are less than 7. So we get 6 out of 6, which is just 1 there. And these last two are kind of important because what I'll tell you is that the probability when you calculate it has to be somewhere in the range from 0 to 1. And you can include 0 and 1 in that range because we can see we got those two possibilities, but you can never have more than a 100% chance of something happening, or we would never have a negative percent chance of something happening. So when we calculate our probabilities, if you have a fraction where the top is bigger than the bottom, that's a problem because that means you're telling me that there's more than a 100% chance that that event will happen. Let's go over to the card examples over here, and you can use the info that we wrote down at the top if you need to. Probability that we get a black card is 26 out of 52, or if you're really confident with cards, you could just say 1/2 there. There are 4 aces in a deck, so probability that that happens will be 4 out of 52. Probability that you get a red king. There are 2 red kings in the deck. It's the king of hearts and the king of diamonds, so that would be 2 out of 52. Probability that you get the 10 of spades. That's a really specific card, so there's only 1 of them in the deck out of 52. Probability that you get a number less than 5. If you look at our list, I know that depending on what game you're playing with cards, sometimes ace might count as 11. Like, for example, the game blackjack or something like that, ace can be a high card. But if you look at the way I listed the cards for you, ace is at the beginning. So ace can sometimes also represent the number 1 in a deck of cards. So for this example specifically, when I say a number less than 5, I'm going to, for now, include ace in that list. So we have ace, 2, 3, and 4. All those numbers are less than 5. And we have that for all 4 suits. So there's a total of 16 cards in the deck that are less than 5 over the sample space of 52 again. And then the probability that it's not a face card. So we know the probability that it is a face card because we know that there's 12 in the deck. So if we do just quickly 52 minus 12, that would become 40 cards in the deck that are non-face cards out of the 52 total. So just read that stuff kind of carefully there. If you have the information correct at the top, calculating these probabilities isn't so bad. Okay. Let's quickly go through the last few here. In the third example, there's 4 different words that are given to us. It almost looks like a multiple choice question, but we're going to do 4 different probabilities. Find the probability that the selected letter will be an O. So picking an O is the event that goes on top. So for example, in the word poster, there's only 1 O, but the sample space on the bottom is the total number of letters we have to choose from in this word, which in this case, poster has 6. So moving on to the word carpool, if I want to choose the letter O, there's 2 options now. Carpool has 7 letters total. So the probability that we pick an O in that word would be 2/7. Robot would be 2/5, 2 O's out of 5 letters total. And cocoon, my daughter's kindergarten teacher is growing butterflies at home, which is very nice of her. I don't think I would be that nice to grow butterflies in my house, but she's a great teacher and doing that for her students from home. So cocoon, there would be 3 out of 6, or actually a 50-50 shot. 1/2 would be the probability that you pick a letter O at random from the word cocoon. In probability, it's kind of also another classic example is having marbles in a bag and choosing them. So in this case, we have 5 red, 4 white, 3 blue. Let's just quickly list that the total number of marbles would be 5 plus 4 plus 3, which is a total of 12. So what's the probability that I pick a blue marble? There's 3 blue in the bag out of a total of 12. Probability that I pick a green marble. Well, I'll read it quickly again, but I didn't see any green marbles in the bag, so that would just be 0 out of 12. If you just want to write 0 there, that's acceptable. And last one is a marble that's not red. So there's 5 red in the bag, so just add up the other ones that are not red. 4 plus 3 would be 7 out of 12. And that would be that probability there. Lastly, number 5, there are 14 girls and 15 boys in a class. If the teacher calls on one student at random, what is the probability that the student is a girl? So the way we're going to calculate this probability finally is take the number of girls that goes in the numerator, that's the event, is picking a girl. Remember that the bottom is going to be the total number of students in the class. That's the sample space. So the bottom, even though it doesn't give it to us right away, 14 plus 15 students would be a total of 29 students. So the chances that I pick somebody randomly and it's a girl would be 14 out of 29. So I'm hoping that today somewhat seemed familiar, because I'm thinking this probability stuff is some things that you've seen in the past, but we're definitely going to be building upon this in the next few lessons. So don't forget, probability homework 1 will be posted tomorrow. Please make sure you complete that and submit it on time. Thanks, and let me know if you have any questions.